This conference will now be recorded.
Hello everyone. Last day we have started chemical properties of haloarenes, that is when halogen is attached to any aromatic system. Now under this heading there will be different types of reactions, and the first one is nucleophilic substitution reaction, then there will be electrophilic substitution reaction, and then reaction with metals. But here, before starting nucleophilic substitution reaction, we have to know that these reactions are not very common in haloarenes, unlike electrophilic substitution, which is more common compared to nucleophilic substitution. But what are the reasons behind this, that why nucleophilic substitution is not so common, that we will discuss. And one point we have already covered in last class, and rest of the points now we will see. So in today's class, first we are discussing nucleophilic substitution reaction, why it is not so common, and then we will see the actual examples of this reaction. Then electrophilic substitution. After that, the third reaction is reaction with metals. Then there will be some related problems, and if time permits, there will be also polyhalogen compounds discussion related to it. So the first point is sp2 hybridization, for which nucleophilic substitution is not so common in haloarenes. Now, next point, instability of phenyl cation. Now, when we are saying phenyl cation, that means positive charge is present over phenyl ring, that is directly on any of this carbon there is positive charge. This phenyl cation, if it is formed by self ionization of ARX, that means if you have any haloarene, in general I am writing ARX, then after dissociation of this, because this type of dissociation you have already seen in case of Eisenberg mechanism, in case of nucleophilic substitution in haloalkanes, that is aliphatic molecules. But if the same thing happens here, what will happen? You will get phenyl cation like this, Ar plus if there is any substitution, or it may be pH plus if it is simple benzene ring. But this type of self ionization will not be stabilized by resonance. Fine, because if the positive charge is present at the benzylic position, suppose there is CH2 group and then positive charge, then it is very stable, because this positive charge can take part in resonance with the double bonds of benzene ring. But if the positive charge is directly on the carbon of benzene, now by resonance stabilization is not possible. So it is highly unstable, and not just resonance, it is it is present on the carbon which is sp2 hybridized, that means which is very electronegative. So because of these reasons, SN1 mechanism, it is ruled out. It is not possible, because we know in SN1 mechanism, first the bond between carbon and halogen is broken, there is positive charge generation. But if it is in case of haloarene, there will be formation of Ar plus, which is not stable, there is no resonance possible, and it is electronegative carbon on which the positive charge is present. So because of these two reasons, SN1 mechanism is not possible. So that is also one of the reasons for which nucleophilic substitution is not so common. So this is number one reason. This is second point. The third point, repulsion. Now, as we are discussing nucleophilic substitution, that means the attacking reagent, that must be electron-rich species. Now, what is mentioned here, it is less preferred for electron-rich nucleophile to approach electron-rich arenes because of possible electronic repulsion. Now, as we are talking about haloarenes, so there is pi cloud present above and below the benzene ring. See, if I am drawing the benzene ring like this, there is pi cloud above and below, and the nucleophile, when it will try to attack here, there is also negative charge in the pi cloud and also negative charge in the nucleophile. So as a result, what will happen? Now there will be repulsion between these two negative charge, and because of this repulsion, when nucleophile will try to approach towards benzene ring, that will not be very favorable process. So this is a third reason. Now, if because of all these reasons it is not so common, then why we are discussing it? Then when it is possible, that is the main question. When nucleophilic substitution reaction is feasible in haloarenes, in spite of so many problems, still it occurs sometimes. Though it is not common, but still it occurs. Question is when it occurs. Now the reason that is answer will be when the aromatic ring is electron deficient. Now as the attacking species is nucleophile, that means it is electron rich. So obviously when it is attacking towards aromatic ring, if the aromatic ring is somehow electron deficient, how that is possible? If there is presence of some electron withdrawing group, for example nitro SO3H. So if there is some group attached to the benzene ring which is highly electron withdrawing, it will decrease the overall electron density by attracting electron density towards itself, and as a result now nucleophilic attack, that is the attack by nucleophile, that will be feasible. But remember, it must be present at ortho and para position. So if that is the nucleophile, if it is entering, suppose it is entering at some particular position, so compared to this position, the position of these electron withdrawing groups, whether it is NO2, SO3H or some other groups, but it is electron withdrawing, this position it must be either 1,2 position or 1,4 position. Then only nucleophilic substitution reaction is possible. Fine. Now we will see one by one different types of examples for nucleophilic substitution. The first example, here the starting material is chlorobenzene. Okay, simple, there is no substitution, only halogen, it is directly attached to benzene ring. And we have taken reagent sodium hydroxide. Now look at the conditions. This is very drastic condition. 623 Kelvin, which is very high temperature. And also look at the pressure, 300 atmosphere, that is also very high. So both temperature, pressure is very high. That means the condition is very drastic. And here the reagent that you are seeing NaOH, but actual nucleophile is HO minus, which will attack at this carbon. Cl will be replaced and the position of Cl now it will be taken by OH. And this is known as Dawes process. The halogen of haloarenes can be substituted by OH, NH2 or CN. So all these are basically the nucleophile which will be attached with appropriate nucleophilic reagent. So if you want to replace Cl or halogen with OH, you can use KOH or NaOH. If you want to replace it with NH2, then you can use ammonia. If you want to replace it with CN, you can use NaCN or KCN. So different types of nucleophilic reagents you can use, but remember condition must be high. So in the previous slide, what we have mentioned, remember in the last this black color box in the right hand side and below, here it is mentioned when electron withdrawing groups are present. So this is one condition when it is possible. But suppose if electron withdrawing groups are not present, it is simple benzene, then obviously you have to use drastic condition, that is high temperature and pressure. So that is why, as there is no electron withdrawing substituent, we are using high temperature and pressure. But this is number one reaction. Look at number two reaction. Now it is not simple benzene ring. One NO2 group is already there, right? That means compared to the first reaction, in the second reaction it will be comparatively facile process. Now compare the temperature, it is 623, but in this case it is 443. So now it is decreased. That means less drastic condition will it will be okay, and Cl is replaced by OH. In the third equation, now another electron withdrawing group is there. So now compared to equation 2, if you see equation 3, temperature is 368. That means now the ring is more deactivated. So the approach of HO minus towards this carbon containing chlorine, that will be very facile process. Fine. And when there are 3 NO2 group, now simply warming it with even we are not using any bleach, water will work. Then also we can replace Cl with H. And if you want to know the that is mechanism, it will be like this. So I'm showing it with the simple molecule which is without any substituent. So there is negative charge over ortho position. Now the negative charge, it can also be at para position if you consider the resonance structure. Now you can get answer of one question. In the previous slide, as it is mentioned that when electron withdrawing groups are present at ortho and para position. See, in equation 2, it is at para position with respect to the OH group or Cl. Then in the equation 3, it is also ortho and para. And in case of 4, it is 2 ortho and 1 para. So always it is at ortho and para position. It is never at meta position, right? Now the reason behind it is that if you look at this resonance structure that I have just drawn in blue color, negative charge is present at 4 position and at 2 position. You can further draw the other resonance structure where you will see the other ortho position, that is if I number it as 6, there is also negative charge. That means negative charge accumulated at ortho and para position. So that is the reason if electron withdrawing groups they are present at ortho and para position, they can balance this negative charge by withdrawing it towards it. So that is the reason only when electron withdrawing groups are present at ortho and para position, then only they will be able to make the benzene ring deactivated so that the nucleophile can attack easily. And finally, what will happen? As I considered, okay, let me draw the other resonance structure. Now rearomatization will take place and OH will be removed. So finally, sorry, not OH, Cl will be removed, and finally we are getting OH in the position of chlorine. So this process is known as dose process. So no effect on reactivity of haloarenes is observed if the electron withdrawing is present at meta position. So suppose if you consider structure like this, that is chlorine, NO2 group present at meta position. Now if you compare this and with this para product, this is para, this is meta. Now obviously the in case of para, NO2 group, it will be able to show its electron withdrawing effect. But when it is at meta position, obviously compared to chlorobenzene, it can somehow deactivate because still it has the minus I effect. But when it is at para position or ortho position, both minus R effect as well as minus I effect, both will be applicable. But when it is at meta position, only minus I effect. So that is why when electron withdrawing groups are present at ortho position or para position, then only the effect will be very important. And nucleophilic substitution will be easier process compared to the situation where you do not have any electron withdrawing groups. So which is clear, as you can see, the temperatures are gradually decreasing. That means less drastic condition will also work. Some more examples. Bromobenzene in presence of CuCN. Here the attacking nucleophile is cyano. We have taken pyridine as solvent. Temperature again it is high, 475 Kelvin. So Cn minus, it will attack this carbon and Br is replaced by Cn and there is formation of CuBr. Next again chlorobenzene in presence of aqueous ammonia. Temperature 200 degrees centigrade. So when it is mentioned in Kelvin 475, just subtract 273. It is also around something around 200, right? So that means same type of temperature. This is also high, this is also high. Pressure is high and we are using Cu2O. And Cl is replaced by the nucleophile which is NH2 minus and that is generated from ammonia. So the Cl that is removed, that that is now interacting with copper plus. CO2 means it is source of copper plus. So here it is making this type of salt. And finally we are getting aniline, that is NH2 attached with benzene ring. It is known as aniline, starting from chlorobenzene. Here we have a problem. Ease of nucleophilic substitution among the following compounds upon treatment with aqueous NaOH will be in the order as. Ease of nucleophilic substitution means how easily the nucleophilic substitution is possible with all these molecules in option 1, 2, 3 and 4. So all these molecules in 4 options, they will be acting as starting material. And what reagent you are using? You are using aqueous NaOH. So basically here the nucleophile is hydroxy R. Here we have different order for these 4 molecules. Now if we look at these 4 molecules carefully, there is a major difference with compound 4 compared to the rest of the 3, because in rest of the 3, 1, 2 and 3, chlorine is directly attached to aromatic ring. That means it is haloarene. But the last one is benzyl chloride. It is not haloarene, it is haloalkane. And we know that for aliphatic halogen compound, nucleophilic substitution is always favored. So it is one thing is clear, that 4 will give you the best result among these 4. That means option A or option D among these, any of these 2 will be correct. So B and C you can cancel just based on this information. Now if 4 is at first, next what we will do, now we will focus on 1, 2 and 3. Now in 1, 2 and 3, in case of 3 there is no substituent. In case of 2 there is electron withdrawing substituent which is nitro, and in case of 1 there is electron donating substituent which is NH2. And we know when we are considering aqueous NaOH, that means it is nucleophilic substitution. So obviously electron withdrawing group, if present at para position or ortho position, it will favor the reaction. So that is why after 4, the next molecule which will give very good result is compound 2, because there is electron withdrawing group. So after 4 it is 2. Now after 2, which one? 1 or 3? Now among 1 and 3, in case of 3, no substituent. In case of 1, there is donating substituent. Now if electron withdrawing substituent, it is having some favorable effect for this reaction. So obviously when it is electron donating group, it will have the opposite effect. That means donating groups will not work. So after 2, the next molecule that you have to choose, if we consider ease of nucleophilic substitution, it will be 3. And at last it will be 1. So correct option will be the first option. So for aliphatic, if we compare aliphatic nucleophilic substitution with aromatic nucleophilic substitution, that means aliphatic is for haloalkane and aromatic, that is for haloarene. So obviously aliphatic nucleophilic substitution is always favored. So based on this, we have chosen that 4 will give the best result. Now after 4, you have to consider electron withdrawing group or donating group. So electron withdrawing group, it will make SNARN. Basically this is a short notation for aromatic nucleophilic substitution. Okay, short form of this aromatic nucleophilic substitution. This is aromatic nucleophilic, S for substitution. So electron withdrawing group, it makes aromatic nucleophilic substitution easier, and donating group, obviously it will do the reverse effect. So that is the reason, first 4, then 2, then 3, and at last it is 1, because there is electron donating group. After finishing nucleophilic substitution reaction, the second type of reaction that is observed for haloarene, this is electrophilic substitution. Now compared to nucleophiles, now the attacking reagent, it will be electrophile, that is it is electron deficient species. And electron deficient species, it is always better, because now as we are considering benzene ring with which some halogen is attached, so this ring is already electron deficient. Sorry, it is already electron rich because there is some pi cloud present above and below the benzene ring. Now, if it has this type of structure, obviously electron deficient species, it will be very easily attracted towards benzene ring. Fine. So that is why electrophilic substitution is always favored. Now for halobenzene, because our main topic is electrophilic substitution for haloarenes. The rate of electrophilic substitution for haloarenes, it is lower compared to benzene. So suppose you have taken simple benzene, there is E plus, you are treating it with some electrophile and you are getting product like this. So here H is replaced by some electrophile. So this is for benzene. But suppose you have taken halobenzene, okay, and you are using some E plus. Now it is not that X will be replaced by E plus. Try to understand the difference. In nucleophilic substitution, what you have seen, in that case directly halogen is replaced and the same position electrophile is coming. But in this case it is different. So when it is electrophilic substitution reaction, basically what happens, now you have to consider what is the whether it is orthopara orienting or meta orienting. Now halogen, they are basically orthopara orienting. That means E plus, that will be attached either at ortho position or the para position. So it is not that X is directly replaced by E. No, that is not the case. Here the hydrogen that will be present at ortho or para, that will be replaced by E. So they are orthopara orienting. But in the first line it is mentioned that compared to benzene, in case of halobenzene, substitution is the rate of substitution is lower. Reason is the ring is deactivated because of minus I effect of halogen. So if you simply compare benzene ring with halogen substituted benzene ring, so obviously in halogen substituted benzene ring, because of the minus I effect of halogen, now the ring will be to some extent deactivated compared to simple benzene ring. Now when it is deactivated, means what? It is electron, that is the electron density, that is now to some extent less. So obviously the attraction towards electrophile, that will also be less. So that is why it is mentioned that rate of electrophilic substitution of halobenzene compared to benzene is lower, because now the ring is deactivated, and that is because of minus I effect of halogen. So this is all about the speed of the reaction, that is compared to benzene. In case of halobenzene, how fast the substitution will take place, that is mentioned in the first point. Now come to the second point. In the second point it is mentioned that because of resonance involving the lone pairs of halogen, electron density increases at ortho and para position more compared to meta position. So look at this picture. This is halobenzene. Now we know there are 3 lone pairs. Now if this lone pair is taking part in resonance, there is electron density now at ortho position. Then further resonance, suppose this is structure 1, this is structure 2. In structure 2, negative charge is present at para position. In structure 3, again it is present at another ortho position. And finally in structure 4, this is same as the first one, but now the position of double bonds are altered. So this is as if the resonance hybrid, that is if you take mix all these 3 structures, if you take the average, it is the average resonance structure, where you can see there is partial double bond nature between carbon and halogen, and also partial negative charge present at ortho and para position. So that is the reason when you are treating it with some E plus, that is electrophile, obviously attraction will be towards this ortho position or para position, because electron density compared to meta, now in these positions it is high. So that is the reason they are orthopara oriented. But remember, they are deactivated. So reactivity is controlled by stronger inductive effects. So when you are considering how fast the reaction will occur, obviously you have to consider the minus I effect. And that is the reason that compared to simple benzene ring, now in case of halobenzene, the speed of reaction decreases. But if you are considering orientation, not rate of the reaction, that is controlled by inductive effect. And orientation, that is the attacking reagent, that is the incoming electrophile, what will be its position? Is it ortho or para or meta? So the answer is now it is ortho-para position where the E plus will be attached. And the reason is that you can already see in these resonance structures because electron density is high at ortho and para position. So that is why it is ortho-para oriented. So here we have example of nitration for chlorobenzene in presence of the mixture of concentrated H2SO4 and nitric acid, which is basically the mixture used for nitration. And here the electrophile that will be generated, that is the E plus, that is actually NO2 plus. So as it is ortho-para orienting, so NO2 will be inserted either at ortho position or para position. So this is ortho product which is minor and the para product that is major. Now the reason why it is major because of steric hindrance. So here two groups are side by side, so there will be some steric problem. But here it is far from each other, so that is why it is the major product. Fine. So from this reaction, it is clear that they are ortho-para orienting group. After nitration, next reaction is sulfonation. Now we are using only concentrated H2SO4 and heat, no HNO3. Here the electrophile is SO3H plus, which is coming from H2SO4. This is minor again, ortho. This is major. But you are getting ortho product and para product, both. Now halogenation of haloarenes, that means already one halogen is there and you are using another halogen or same halogen, it may be bromine also. So this is halogenation reaction of haloarenes. We are using chlorine and here catalyst is required, which is anhydrous FeCl3. Now this catalyst, it is actually Lewis acid catalyst. It is what it does. Lewis acid means it is always searching for some electron density because it is itself electron deficient. So Lewis acid simple definition is it is electron pair acceptor. Now if you simply write chlorine molecule, diatomic molecule, it is like this. Now both sides there is same atom. So how the electrophile will generate? So this catalyst actually helps to generate the electrophile. And how it does so? FeCl3, what it will interact with one of the chlorine and it will make this CCl-Cl bond very weak. As a result, what will be generated? Cl plus will be generated from the left hand side and this chlorine will be attached to FeCl3 as Cl minus and ultimately it will make FeCl4 minus. So in this way, the electrophile is generated with the help of FeCl3 as catalyst, and that is the reason why it is used. Now this is the electrophile, but electrophile will be inserted in para position or ortho position, and para as usual it is the major one. Friedel-Crafts reaction. Now this is very important reaction, and under Friedel-Crafts two types of reaction possible. The first one, it is known as alkylation. Why it is alkylation? Because alkyl groups are inserted. And the second one is acylation. So the first one you will call it Friedel-Crafts alkylation and the second one Friedel-Crafts acylation. So see, in the first case some alkyl groups are inserted because here the E plus is this alkyl group, not just any CH2, it may be other alkyl group also. But in the second case COCH2, so this is acyl group inserted, so that is why the name is different. And what type of reagent we have used as a source of this alkyl group? We have used some alkyl chloride. So for Friedel-Crafts reaction we use alkyl chloride. In general you can write it as Rx, that is any other halogen. And here this catalyst is used, which is also very important. Again it is a Lewis acid catalyst, and what it does, it helps to weaken this bond, because if it is interacting with this halogen, there will be that is this bond between R and X will be clipped. As a result, R plus will be generated, which is actually the electrophile, and it will be inserted in the ortho position or para position. Similarly, if it is CH3COCl, then this bond will be weakened, because AlCl3 will interact with chlorine. It will form AlCl4 minus. So this bond will be broken. There will be generation of electrophile, which is this one. So this is E plus, and it is inserted at ortho position and para position. So here our purpose is to generate the electrophile. And for that purpose, what we have done, we have used some anhydrous catalyst, which is Lewis acid catalyst, and we have used some alkyl halide, that is Rx, and in this case it is RCOX. But see, this is not just limited to this method. If you are applying some other methods by which you can generate E plus, that is you can generate CH3CO, that is RCO you can generate. This is the general electrophile structure for the second reaction. So if somehow you can generate R plus or RCO plus, then also it will work. So it is not just always limited to the use of Rx and Lewis acid catalyst. You can generate it by some other methods also. So just for example, another method which is very common and which is used for generation of electrophile. Sometimes, suppose you want to generate the electrophile Me2CH plus. So normally what you will think, that for this I will use Me2CHX, but you can use something other also. What you can use? You can use propene. Now this is alkene. Then how it will be generated? That is how Me2CH will be generated. Now for that purpose you have to use some concentrated H2SO4. That is, you have to protonate this. So in presence of H plus, this negative charge, it will be attracted toward H plus, and a positive charge will be generated here, which is nothing but Me2CH, same. So in this way also, that is alkene and concentrated H2SO4, in this way also you can generate electrophile. So basically, somehow you have to generate this carbocation for Friedel-Crafts alkylation, and for acylation you have to generate this type of electrophile. So be very careful whenever any question is given. So just look at the reagent and you have to think that from this reagent, what actual electrophile or nucleophile can be generated. That you have to be very careful. So it is not that Friedel-Crafts reaction always means you are using some Rx or Lewis acid mixture. No, it is not limited to that. There are some other way also by which you can generate electrophile. Reaction with metals. So the second reaction type, that is electrophilic substitution, that also we have covered. The first one was nucleophilic substitution. The second one electrophilic substitution. Now we have reached towards the third one, which is reaction with metals. The first example that you are seeing here, two molecules of haloarene we have taken in presence of 2 sodium and solvent is ether. So as if the reaction is like this, PHX, 2 sodium, another PHX. So this part is removed and there is direct PH. These two groups are attached. So this is diphenyl. It is also called biphenyl. And NaX is removed depending on what X you have taken. Now this is Wittig reaction. Another example is Wurtz-Wittig reaction. Now in Wurtz-Wittig reaction, remember this term you have already heard, Wurtz reaction, where we this reaction we have used in case of haloalkane, where we have taken two Rx. It may be same Rx or different R group, Rx and R prime X, and you have used the same condition. So keeping that in mind, you can find some similarity, but here one reaction partner is aromatic, that is haloarene, Another reaction partner is haloalkane, and these two sodium it is used, but important point is one sodium will react with X, it will make NaX, another sodium will react with this X, it will make another NX, and ultimately this phenyl group and R group, it will be attached to each other. So suppose if it is CH3Cl, you will get toluene, that is benzene ring CH3. So this is Wurtz fatigue, and when it is fatigue, there is only halogen. This is the difference between these two. Another example, reaction with metals. Now see, these reactions we are discussing under reaction with metals, because here we have used sodium metal in first two reactions. Now in Ullmann reaction we have used copper powder, and iodobenzene is the starting material. Here also these two benzene ring, two molecules that will be attached. So carbon-carbon bond formation is there. Grignard reagent. Now Grignard reagent we have already discussed in the last class in detail under the heading of reaction with metals. That is the same type of reaction, but that is for haloalkanes, not for haloarenes. But Grignard reagent you can also make starting from haloarene. So that is why same reaction you can see here. But here instead of taking aliphatic halogen, now we have taken aromatic. So this is bromobenzene in presence of Mg ether, same condition. That is the same condition you have used for haloalkane. The same condition we are using now also. So magnesium in presence of ether, we are getting PHMgBr. You can also write it as. So this is phenyl magnesium bromide. Now related to this, we have a problem here. The major product of the following reaction that we have to find. Now the starting material that you can see here, we have aromatic ring. There is isopropyl group. At meta position there is CH2CO, then CH2CH2Cl. The first reagent we are using potassium tertiary butoxide, which is very strong base. And the second reagent we are using concentrated H2SO4, that means acidic condition along with heat. Now if you look at the substitute, that is the starting material, it is having aromatic ring, then there is carbonyl group, and also there is a chain, alkyl chain, and then chlorine. That means it is haloalkane also. That is this part, if you observe mainly, it is just like haloalkane. And haloalkane, when it is in presence of strong base, elimination reaction is highly favorable method, right? So here elimination reaction will take place. That is beta elimination. With respect to chlorine, this carbon is alpha, this carbon is beta. So beta hydrogen and chlorine, these two will be removed. There will be formation of CC double bond. Isopropyl group. So in this part there is no change. After removal of this H and Cl, there will be CC double bond generation. So this is the first structure that you will be getting after treating it with potassium tertiary butoxide. Now in the next part, there is use of concentrated H2SO4. Now if you look at the molecule carefully, protonation is possible at CC double bond, and it is also possible at the position of oxygen. And here isopropyl group is present, which is having some donating effect. That means this benzene ring that you can see, it can act as a very good nucleophile. That is, a benzene ring itself will act as nucleophile, and if there is any positive center generated in the molecule, it will be attracted towards this. Now as in the second step, H plus is present in the medium, this type of reaction, that is double bond shifted here, this type of reaction, that is highly possibilities there. So now what you are getting, O minus double bond plus. So now any separate electrophile is not there in the reaction, but within the molecule there is presence of electrophile. So this is actually the electrophile. Okay, and any alkyl group, they are always orthopara orienting. So that is the reason why orthopara orienting, that I will show here. So with respect to isopropyl, this is ortho position, this is ortho position, this is para position. But if it is attacking through ortho position, there will be steric hindrance, so it will always prefer the para position. So attack will be through para. So double bond shifted, this double bond is attacking here. Now what will be, ring structure will be formed. But if you are having trouble to understand the number of ring, whether 5 members, 6 members, 7 members, just put number 1, 2, 3, 4, 5, 6. So here carbon number 1, it will be attached to carbon number 6. That means a 6-member ring will be generated. And after this double bond is shifted, there is positive charge, which is highly stabilized by this donating group, which is alkyl. So that is why it is orthopara oriented. So this will be the structure that you are getting. But remember, in this structure, the aromaticity, it is lost. So you can regenerate the aromaticity, and that is possible if you consider this hydrogen. So this H will be removed, that is minus H plus. So now aromaticity is regenerated. And here the O negative that you are seeing, this O negative, it can take this H plus which is removed. That is this H plus, now it can be attached with oxygen. So I am writing it, removing this negative charge and writing H here. So if you look at this portion only, this is actually enol type of structure. So enol can be easily converted to keto form. So isopropyl group is there. And after changing to keto form, now it will be like this. So see, this is matching with option 3. So another possibility also I have mentioned, that if the attack is occurring through ortho. Now if it is occurring through ortho, then also there will be 6-member ring formation. So in that case, this should be the structure. But ortho, it is always sterically hindered, because if you compare the structure 1 and 3, obviously 3, these two groups, they are far from each other. So that is why 3, that is para product, that is always favored. And option 2 and 4 not possible, because here 5-member ring is generated, which is not at all possible. Possibilities 1 and 3, but 3 will be favored because of the fact that para is major. Next we will go to next question. Here the starting material, one bromine is directly attached to a benzene ring, that means it is as if haloarene. Another bromine is attached to 3-member alkyl chain, which is at meta position with respect to the bromine, which is in aromatic ring. The first reagent we are using potassium hydroxide, aqueous. Next reagent is chromium oxide H plus, acidic condition chromium trioxide. Third reagent is acidic condition H2SO4 along with heat. Now remember, KOH, whether you are using alcoholic condition or aqueous condition, depending on that, it may be substitution or it may be elimination. So when it is aqueous, it is basically substitution. And substitution, it is favored for aliphatic halogen. So this bromine will be substituted, not this one only. So the first step is, in presence of KOH, you will get OH. Next reagent is oxidizing agent CrO3H plus. Here what will happen, this CH2OH group, which is 1 degree alcohol, CH2OH group, that will be converted to COOH because we are using some oxidizing agent. But this is not end of the reaction because you are also using some acidic condition. Now, in acidic condition, protonation is possible to this oxygen. Now, when protonation is possible, you can get structure like this. So oxygen is now positive, but you can also draw another structure which is so the positive charge, it may be here also, and bromine is here. Now, what we know, for haloarene, it is ortho-para orienting. So with respect to the bromine, these two are ortho position. This is the para position, and para position is always favored. And here also, this part is basically acting as electrophile. So within the molecule, there is electrophile. There is no separate electrophile, as if it is intramolecular electrophilic aromatic substitution. And bromine, as it is ortho-para orienting, sorry, it is not like this. Let me draw it clearly. And show it here. Positive charge is there. And with respect to bromine, this position is para. So this will attack this carbon. Now again, just put number if you are having any issue with the number of ring that is formed. 1, sorry, this is 2, this is 3, this is 4, this is 5. So 1 and carbon and 5 carbon, these two will be, there will be CC bond formation. So the structure that you are getting, now bromine is positively charged and there is ring structure formation. Finally, as aromaticity is lost, this H, it can be removed in the form of H plus, that is minus H plus, and you can gain aromaticity back. And now there is a 5-member ring attached. But this is geminal diol. Remember, geminal diol is when single carbon is containing 2 oxygen. And for any geminal alcohol, they are not very stable. So what happens in this type of structure? One OH bond is broken and it is another OH is removed. So finally what you get? You get CO double bond. So same thing will happen here. So finally there will be formation, this part will be removed. And there will be formation of carbon. So it is matching with which structure? Obviously these two are not possible because OH is there. But in our case, Br is still attached to aromatic ring. So among 2 and 4, one will be correct. Now option 4, this will be the correct structure if the attack is to ortho position. So this is basically the ortho product. But option 2, that is actually the para product. And para product is the major product. I am not saying that this will not be formed. But here you have to find the major product. Always if it is single choice answer, always go for the major product when there is a possibility of generation of another minor product also. And you should also know that option 4 is also one of the possible product because sometimes it may be more than one answer is correct and you have to choose that is multiple correct choice. So in that case, If it is asking that what are the possible products, so in that case both 2 and 4 you have to select, because both will be actually formed. But as this is the major one, so that is why we are choosing it in this case, because it is single choice. But you should also know that option 4 is another possibility which will happen. You can also follow the same mechanism that I have shown here, but now it will be through any of these ortho position. The attack, that is the electrophilic attack, that is not through ortho position but through para position. So you can draw the mechanism yourself. In that case you will reach the answer option 4. But we are rejecting this option because it is the minor product and we have to choose only one option as the correct. So that is why we are choosing it. That is option 2 is the correct option. So after finishing all the chemical properties of haloarenes, now we have another topic which is polyhalogen compounds. Polyhalogen, as the name suggests, obviously there will be more than one halogen, right? That is why the name polyhalogen. The hydrocarbons or any carbon compounds that contains more than one halogen atom, obviously they will be called polyhalogen compounds. Now many of these compounds have significant application in industry and agriculture, so that is why they are so much having importance. The first structure under polyhalogen compound that we are going to discuss is this one, CH2Cl2. Now this is derivative of methane, because methane having structure CH4 where you have 4 CH bond, but if 2 CH that is H is replaced by Cl, then you will be getting the structure CH2Cl2. So CH4 is tetrahedral, this one is also a tetrahedral, carbon is sp2 hybridized, and two types of name you can use. You can call it dichloromethane because after all it is methane derivative. You can also call it methylene chloride because the group methylene is CH2. So CH2 group is there, but rest of the 2 valency of carbon out of 4 that is satisfied by chlorine. So that is why it is methylene chloride. So this molecule, it is geminal organic compound because both chlorine, they are attached to same carbon. Remember last question we have discussed geminal alcohol, but now it is geminal because of same group attached to same carbon. How we can make it? That is naturally, if we consider how it is naturally produced, it can be obtained naturally from oceanic sources, macroalgae, volcanoes, wetlands. Though the majority of these compounds is found in the environment due to industrial emission. Okay, it harms the human central nervous system. So this industrial emission by which this is produced, this is not at all desirable. Now, what are the application of this molecule? Aerosol spray propellant, solvent in paint remover, degreasing agent to remove grease. Then to make some pharmaceutical product, this can be used as solvent. Remember, we use CCl4 as organic solvent. So this is also as if just like CCl4, only difference you do not have 4 chlorine but 2. But this is polyhalogen and used as a metal cleaning and finishing solvent. So you don't have to remember particularly or the application, but remember it has industrial application. But for human, as it affects central nervous system, this is harmful. The next molecule, which is also polyhalogen, now see same structure, but another chlorine is also there. So that is why it is CHCl3, trichloromethane. The previous one, dichloromethane, now it is trichloromethane, 3 chlorine. Now chloroform, which is mostly the name we use, important trihaloalkane. Why it is alkane? Because after all it is methane derivative, alkane derivative. Initially its use was mainly for anesthetic, but this dense liquid it is produced on a large scale for that purpose. And Dumas, that is the name of scientist, named CHCl3 as chloroform because it gives formic acid, that is ACOOH, when it is hydrolyzed. So because of that fact, its common name is now chloroform. Preparation method, how you can make it. Chloroform is prepared in laboratory by heating a mixture of bleaching powder either with ethanol or acetone. The first method that we are going to see, how you can get it by using bleaching powder and ethanol, and the second method will be bleaching powder and acetone. Basically, ethanol is also 2-carbon compound. This is also 2-carbon compound. Sorry, 3-carbon compound, but here 1 carbon will not be required. So we need 2 carbon. So here the first method, which is bleaching powder and ethanol. First step is bleaching powder, CaOCl2. Actually, the structure is something like this. Calcium, OCl, Cl. So CaOCl2, it is written in this way. First, it is hydrolyzed. What you get calcium hydroxide and chlorine molecule. In the second step, you have taken ethanol in presence of the chlorine, which is already produced in the first step. There is oxidation reaction going on. So from alcohol, now you are getting aldehyde and HCl, 2 molecules. The third step is, now this aldehyde again reacting with some more chlorine molecules. There will be chlorination. See here, all the 3 hydrogen replaced by 3 chlorine. So it is now CCl3CHO. The structure is like this: Cl, 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 CHO, CCl3CHO and HCl. Finally, 2 molecules of CCl3CHO and this calcium hydroxide already produced in the first step. It will now react and it will make CHCl3. So as if CHCl3, you are getting 2 molecules from here, 2 oxygen extra, and here we are getting calcium formate. Formate ion is HCOO-. So 2 formate ion is there and calcium. So this is the first method. And the second method is, again you have taken bleaching powder, then reaction with water, formation of same thing. First step is same. Second step, now we have taken acetone. In presence of chlorine, there is formation of trichloroacetone. So acetone is H3C, COCH3. But if suppose any one of this methyl, it is converted to CCl3, it will be called trichloroacetone. Now 2 molecules of trichloroacetone in presence of calcium hydroxide already produced in the first step, it will produce CHCl3, 2 molecules, that is our final dessert product, and calcium acetate. So in the previous case, there is formation of calcium formate byproduct, and in this case it is calcium acetate. So it will be acetate ion is CH3CO-. So 2 of this molecule, it will be attached to calcium. So here 1 carbon is extra compared to the previous reaction, because in ethanol you have 2 carbon, in acetone you have 3 carbon basically. So 1 carbon will be extra because our dessert product is same in both cases. So in this way, by using these 2 methods, we can prepare chloroform. So this is not the end of chloroform. We'll also see its application in, and also some other polyhalogen compounds in the next class. So we have reached at the end of this class. Thank you for this.